Okay, everyone, let's get started again. Now, we've introduced on the last video Rule 1 and Rule 2, the quotient rule here in Rule 2, and a product rule here in Rule 1. And really, you can sort of kind of get Rule 2 from Rule 1, but I don't want to get too theoretical. And I put a stipulation of x being greater than 0 just to avoid any trouble. There are certain, if m and n are real pretty like integers, you can relax that and let x be negative. For integer m and n, and if m and n are both positive, you can straight up let x be 0. But, we'll talk about that in a few. But let's look at some more examples. Now, you know how I've been using x the whole time? X, you remember x to the 5th times x to the 8th, for example, that would equal x to the power of 5 plus 8 by the rule 1. That's x to 13, no problem, right? But now what if I want to use instead of a monomial x, what if I want to use something a little more convoluted? What if I want to use 3y down here, and I want to do 3y to the 5th times 3y to the 8th. Notice I'm instead of doing x to the 8th times instead of doing x to the 5th times x to the 8th, I'm doing something more complicated to the 5th times the same more complicated base to the 8th. Well, I just proceed like I did before. That's going to be 3y to the power of 13. And I made a mistake over here. I made a terrible mistake. That's x to the 13. I'm sorry, guys. That's x to the 13. Yikes. Error corrected. Yeah. Sorry about that. Error corrected. All right. That's x to the 13. I got ahead of myself. Okay. So now 3y parentheses to the 5th. These parentheses are very important. You need the parentheses. Times parentheses 3y to the 8th. That equals parentheses 3y to the 13th. The parentheses are hugely important. You didn't really need them around x because x was what we call a monomial without a coefficient. If you have a coefficient, you need parentheses. And what if we want to make it even more convoluted? Well, we can. We'll need parentheses. So, for example, what if I want to do? It's going to make me type it in. I need to scroll down the page, and you all might not can see this. What if I have 3y to the 5th? Instead of 3y, what if I do 3y plus 17, just something convoluted? Put a z there. I want to make it really convoluted. Just some convoluted thing to the 5th times that same convoluted thing raised to the power of 8. That's going to equal, that same convoluted thing, 3y plus 17z. And I've got to skip a line. I'm out of room. So come down here where my cursor is, 3y plus 17z raised to the power of, same rule, 5 plus 8, right here. And that's going to equal, the convoluted thing, 3y plus 17z, that is that thing, raised to the power of 5 plus 8 is 13. So, there we go. Now, yeah, you can do more convoluted stuff, right? The rule still applies, when you make it convoluted. Yeah, and we are assuming, that y and z are probably both positive, but, I don't want to get all neck deep into theoretics. And in this example I did a minute ago, I was assuming that y was probably positive. Actually, these are integer powers. Y can be anything it wants. Y could be a negative number here because these are integer powers. Actually, y and z could be negative for all I care here, right? Since we're using integer powers here for this example, y and z could just as well. Y was in this example. Y could just as well be negative, as it turns out. And likewise here, y and z could one or both of them could be negative if we wanted them to be. They don't have to be. When you do integer powers, we can relax the restraint of. So we can relax the restraint of positivity, of base positive, or positivity, the positivity of the base down here, when we have integer powers, whether, whether it's a positive integer power or negative integer power, it doesn't matter. As long as it's an integer power, we can relax the restraint of base positivity when we have integer powers. Yeah. And sure. And of course, I am assuming that we do not get 0 raised to the 0 power, right? And I'm assuming that we stay away from 0 to the 0 power, but that gets, like if you get 0 for an exponent, this is getting a little theoretical, but if we get 0 for an exponent, just be sure, you can get a negative base, just be sure to not get a 0 for a base. Any other base is fine, right? But let's not get too theoretical. If we get 0 for an exponent, let me do good grammar. We want to be sure to avoid 0 for a base, basically. Anyway, my grammar here is probably not perfect, but let's let it go. I'm on a limited time. We want to be sure to not obtain a 0 for a base. Okay. Yeah, I gotta watch my time. Now, indeed, if we use we can use raw numbers, right? Integer powers, we can do like 2. Remember, the law still holds. 2 to the 5th times 2 to the power of, say, 10. That's equal to 2 to the 15. Now, since 2 is positive, we could do what we want. We could use funny numbers. 2 to the power of like negative pi times 2 to the power of, who cares? Let's say 17. Well, that's just going to be 2 to the power of 17 minus pi. Since 2 is positive. Yeah. Now, what about negative 2 for a base? If we use a negative for a base, say negative 2, just because I guess I'm in a mood, I'm in that frame of mind. If we use negative 2, you got to have parentheses. Well, first off, if you use a negative, you got to have parentheses around it. Notice for positive 2, we didn't need parentheses. Well, that's important, but that's not the main idea necessarily, but it's an important point. Anyway, the point I was wanting to get at, we can't use negative pi, right? Don't go using negative pi, but you can use like negative integer, neg 2 to the negative 7 times like neg 2 to the power of, let's say, negative 30. Just whatever. You could have done whatever, just so it was an integer. So that's going to be neg 2 to the power of neg 37. Yeah, that's fine. What's not fine is we just we can't allow things like negative 2 to the power of pi or negative pi to any irrational power, right? We can't allow negative 2 to be raised to an irrational, right? Anyway. Because negative bases, we have to tie them down a little more. And, well, yep. Negative bases must be tied down. Actually, even with rational powers, we must be very careful with negative bases. And indeed, negative 2. Now, negative 2 to the power of a rational number, will it make sense? We got to be careful. Negative 2 to the power of a rational power, if it's in lowest terms, well, let's see. Negative 2 to the power of a rational power, like P over Q, well, makes sense if Q is odd when P over Q is in lowest terms. If P is odd for rational, and this is for rational exponents. So, and this is true for general, yeah. This holds for negative bases in general. So if P over Q is in lowest terms and Q is odd, then you're fine. This will make sense. You can push it on through, and you can do the usual stuff with it. Okay. But life gets a little nasty if or life gets impossible life gets way nasty if you move away from this. In fact, it's invalid. You don't have anything to do with it. Stay away from it. You do not want to let Q be even, right? Stay away. If it's in lowest terms and Q is even, you're in trouble. Now, for positive 2, we didn't care, right? Positive 2, the sky's the limit. We can use irrational, right? For positive 2, we could do what we want. We could do 2 to the negative pi, 2 to the pi. We can do what we want. For positive, we can do what we want. Indeed, if we have if we have something like pi raised to the power of 17 times pi raised to the power of some weird irrational number, let's just call it alpha, where alpha is just some weird irrational number. Well, since pi is positive, right, it's fine, right? It's just pi to the power of 17 plus alpha. And alpha could be some weird irrational number. It could be positive or negative. I don't know. But we don't care. The whole point is the base is positive. Pi is a positive number. We're fine, So, that's when we can, just letting y'all know what I can and can't do. And I'm about out of time, but I'm just wanting to get the weird situations out of the way. But now, as far as 0 is concerned, okay, now concerning the 0 case, if m and n are assumed to be positive real numbers, and not necessarily rational, just positive real, then 0 to the m plus n is 0 to the m times 0 to the n, which is 0. And 0 to the m is 0, 0 to the n is 0, which is all 0. Now again, for positive real numbers m and n, if we assume that m is the bigger thing, m Michigan is greater than n Nebraska, now technically 0 to the negative n is undefined. But however, 0 to the m is 0, and we go ahead and we define 0 to the power of m minus n to be 0. And we can make that definition safely because m minus n is a positive number. It's greater than 0 right here. And this doesn't cause any problems to define it right here where my cursor is. Thank y'all. See y'all next video.